everyone. Thank you for everyone for being here for TERN's webinar, which is on linking drone and satellite acquired data for effective ecosystem monitoring. It's so great to have you. So to start today, and in keeping with the spirit of reconciliation, we at TERN acknowledge the traditional owners and custodians throughout Australia, New Zealand and all nations, and we honour their profound connections to land, water, biodiversity and culture. And we pay our respects to the elders past, present and emerging. Today I'm joining you from Jubugai, rainforest country in far north Queensland. Again, thank you all for joining us today. And for those that haven't met me, my name is Beryl Morris and I'm the director of TERN, which is Australia's Ecosystem Observatory. This is our first webinar for 2023. And I thought I'd like to let you know that there are some 40 countries represented. Woohoo! And we've got 600 people registered. So I hope you're all subscribed to our newsletter so we can stay in touch. And I think that Marianne will be popping a link into our chat. Just a few housekeeping points to start with. For questions to the speakers, can you please use the Q&A function at the bottom of your screen? And we'll answer all the questions towards the end of the webinar, or we'll get in touch with you later if there's something extra that we need to add. If you have any technical issues, however, let us know in the chat function and we'll try to resolve the problem as soon as we can. And as you leave the webinar, we hope you'll take the survey that appears in a separate window. So today we're recording the webinar, and that means that you can revisit the talks or share the link with those that couldn't attend the webinar today. I'd also just mention that TERN has funding from the Australian government and from all the state governments, and we are made up of a very large community, all federated to run observing across the country so that we understand our environment and climate and are able to better make predictions. So now I'm going to introduce you to our speakers. So they're in the order that they're going to speak on the screen, and you would have seen their bios when you registered. So I'm only going to give you a brief introduction so that we can get right into their talks. So first of all will be Professor Ako Lucia, who's from the University of Tasmania, and he's the head of the School of Geography, Planning and Spatial Sciences, and also known as the Professor in Remote Sensing. He's also helping TERN to design its drone programs and helping us set protocols and how we deploy drones. He'll be followed by Dr. Daniel Yiradaya-Kunu, who's an Associate Professor in Marine Science at Deakin University in Victoria. Dan is a marine biologist and he's interested in multidisciplinary and multiscalar approaches to mapping habitat, integrating remote sensing, geophysical and biological data sets. And then we have Dr. Karen Joyce, who's on location today with her drone, and she is Associate Professor at James Cook University in Queensland and is an expert in geospatial science, remote sensing and drones, not to mention having a passion for inspiring school students to learn more about the world of spatial studies, which is great to know. Now I'm going to hand over to Ako and he'll then hand over to Dan and then over to Karen, and I'll see you back in a little while to take Q&A. So I'm turning off now.
Thank you, Beryl, for that introduction. It's great to be here with you today. Just a very quick check that you can hear me okay and see the screen.
Okay.
Thank you. I'd like to acknowledge my virtual co-presenters, Purnima Sivanandam, who's done a lot of this work for TERN, Ben Sparrow, Matt Stenson, and I'd like to thank TERN for financial and logistical support for this project. So I'm going to present to you today some of the efforts of the last couple of years, focusing on developing protocols for drone remote sensing for terrestrial ecosystem monitoring within TERN. Now, the motivation for this work is that is that drones are a fantastic tool, or really have the potential to fill an observational scale gap between detailed field observations and full-size airborne and satellite observations. Drones have the ability to capture really fine-scale information, practically on demand with a range of sensors. And it's really a complementary data source to a lot of the perhaps more traditional data sources we are already familiar with. One of the issues, though, is that in the last decade or so, the drone technology and sensor technology has rapidly progressed. And there's more and more teams using drones in their work and for their data collection. But one of the issues is that data is collected with different sensors, different drones, different sensor settings, and different mission settings. And so there's a lack of consistency. So this work was very much motivated by being sort of more consistent in our data collection and coming up with a robust way to collect ecosystem data with drone technology. And ultimately, the aim is to operationalize drone data collections across the country, across a range of ecosystem plots, and to then use that data set to more systematically monitor our ecosystems and to feed into some of the national and international calibration and validation projects for satellite products. So first, I'll show you some of the hardware that we settled on. So we decided to work with, I'll turn that down a little bit, to work with commercial off-the-shelf drones. The DJI Matrice 300 RTK, because it's a robust platform. It flies for quite a long time. It's still reasonably portable, and it's sort of robust to typical field conditions. We fly that with a full frame mapping camera for RGB imagery and a MicroSense Red Edge MX or dual multispectral camera. We typically fly 80 meters above ground level, resulting in 1 centimeter pixel size RGB orthomosaics and 5 centimeter multispectral orthomosaics. We can see here that the multispectral camera, they've sort of tried to align the bands with typical Landsat and Sentinel wavelengths. It has an incident light sensor, so it can correct for variable lighting conditions. And we cover sort of key portions of the visible and near-infrared spectrum. In addition, DJI teamed up with Livox and produced this ZenMuse L1 laser scanner. It's a solid-state laser scanner that we fly typically 50 meters above ground level or above canopy, resulting in hundreds of points per square meter. And we also developed a data collection protocol for this device. We do fly them separately, so we fly the RGB multispectral camera together in a single mission, and then fly the LiDAR separately in a separate mission. So this project very much focused on the protocols, and the word protocols can sound a bit dull, but I think in the context of ecosystem monitoring, it's really important, because if multiple teams collect data according to set protocols with the same equipment, we actually start to build up a baseline, and then ultimately by following those protocols, we can then be confident that we map and monitor in the same way, and actually pick up changes that perhaps we wouldn't be certain about if we were to collect data, with variable camera settings and so on. So the collection protocols very much focus on the mission settings, so that the drone flies according to fixed mission settings, and the camera and sensor settings. And we've experimented quite a lot with these different settings. The protocols also include post-flight data checking, data backup, and then transfer of data to a central data repository. The processing then focuses on a structure for motion workflow using Egisoft Metashape software to produce 3D point clouds from RGB and multispectral imagery, but also orthomosaics in a consistent way. I suppose the unique thing about our protocols is that they don't rely on ground control points. So we spend a lot of time fine-tuning those protocols so we get really accurate georeferencing and co-registration of the different data products. With a LiDAR data processing workflow, we also have a LiDAR strip alignment, and then we have an automated R processing workflow to derive products like bare ground models, canopy height models, height profiles, and several grid layers. All of this is in the open domain. The protocols have been published. Python scripts for Aegis of Metashapes are available. The R scripts are available. And so they're in the public domain for you and for the community to use. So there's some examples here of the data products to give you a bit of a feel. So first, we did a direct georeferencing trial. So we put out a lot of ground control points purely as external validation. These were measured with geodetic GNSS field equipment. So we picked up these ground control points in the final orthomosaic and 3D models generated by our workflow. So no GCPs were used to generate the ortho. We achieved a horizontal accuracy of 2 to 3 centimeters of the orthomosaic and a vertical accuracy of 10 centimeters, which is really quite remarkable because it really allows us to collect drone data without the need to put out that really time-consuming ground control. And that really speeds up the operational process of data collection and would allow a field mapping team, for example, to take a drone kit as part of their of their field kit. Here's an example. It's quite a dark RGB image, but you can see some wildlife tracks and some branches. So it's an example of RGB imagery, and this is the matching multispectral imagery. And when I flick back and forth, you can see very subtle shifts, but the match between these images is very, very good. And I just want to clarify this, there's been no photoshopping or no PowerPointing, no sort of shifting of images. This is purely done in the automated process of orthomosaic generation. In May last year, we got together with the TERN surveillance team led by Ben Sparrow to test some of these protocols in real conditions and cover a range of established TERN surveillance plots across different types of ecosystems. So that allowed us to practice with the protocols in the field, but also with some of the data generation. So here's an example of a vegetation, of a river gum vegetation community, of a multispectral orthomosaic with a range of vegetation indices that were derived from these. There, the output is in cloud optimized GeoTIFF so that they can be easily shared, can easily be read in by packages like QGIS or image processing packages. This is just a snapshot of that same study site of some of the LiDAR data. So the LiDAR data is colored by RGB colors from the built-in camera. And here's an example of one of the TERN super sites at Calibrating. So it shows quite a large site of about 300 by 300 meters centered around that super site. So a lot of excellent structural detail in that data. We then run it through our automated ground classification process. So we pick up the ground, or we first align the strips, we pick up the ground points, we then grid the ground points into a DTM and then derive a vertical height product. So these are, when I say products, these are GeoTIFFs that then come out of the LiDAR data set. And that's an automated processing workflow in R using the LiDAR package. So those protocols have been published. I'll show you. I'll send the link at the end of this this talk. I just briefly want to talk about what some of the current initiatives are in the last few minutes and our future focus. So we also fly hyperspectral sensors. We have a SPECIM FX10 and FX17 in the visible, near-infrared and shortwave infrared. And with this hyperspectral push-room system, we collect over 170 bands. There's a range of sites here that we've collected before, including a couple of super sites. And the intent within TERN is to collect this type of hyperspectral drone data over key super sites across the nation. So those super sites are really the focus of a lot of ecological research at a wide range of different scales. So hyperspectral data gives us the ability to not just look at those broader vegetation indices, but actually to start looking at traits, to things like photosynthetic activity through PRI, or light harvesting capability, or pigments like anthocyanins and chlorophylls. And so the amazing thing about this is that we can really start to look at this at these traits, these spectrally derived traits in a lot of detail. And that gives us really sort of new insights into the variability of some of these traits at a really fine scale. And that then helps us in turn to better understand the signals in satellite images, especially with some of the upcoming hyperspectral missions, and also better link our field observations to some of those broader scale initiatives. We can also use these traits through trait probability mapping to derive things like functional richness, and use this as a monitoring tool to work out how our ecosystems change over time. Some of the other things we're working on are deep learning techniques and machine learning techniques to really try and extract some of the ecological building blocks out of the raw data. So this includes convolutional neural networks. And one of the things I'm excited about in terms of developing a capability for the future is that I feel we should work towards crowdsourced labeling tools for ecosystem science. So we not only make the data available, but we actually ask the community to get involved in labeling of features that in turn will inform some of the algorithms and improve their transferability. Very recently, and this includes some photos from the last couple of weeks, we're taking these drone sensors and mounting them on light aircraft to get actual genuine multi-scale observations from drones from the air and linking that also to satellite data. So the opportunities are great. I think a lot of the space agencies are producing some of these broader products like frictional cover, canopy height, LAI, and so on. And I think we have great potential within TERN and with these drone protocols to really feed into these monitoring programs. So I'll conclude here. So the intent is to scale up operational data collection, so to have dedicated teams out in Australia collecting drone data. That will enable new research just purely by generating these data sets and opportunities for future monitoring and calibration validation of some of these high-level satellite products that are increasingly generated. We also look at deep learning and machine learning to identify those building blocks in the imagery and focus on some of the super sites to look at the sort of higher level structural traits and physiological traits. So that's some of the ongoing work. I'll leave you with some of the resources that I showed today, including the protocols for you to comment on or adapt or use in your own work, and some of the data collected at Calibrating. And I'll try and put these links in the chat so you can easily access them. So I'll leave it there. Thank you, Beryl. And these are my contact details, so I'll stop sharing.
Thanks, Zarko, and we'll hand over to Dan now.
Thanks, Beryl, and thanks, Arco, for a fantastic presentation. Hopefully this works. Hang on 1 second. I'm just going to share my screen. Oops. Excellent. Can you hear me and see me okay? Can you see my screen?
All going well, Dan.
Fantastic. Look, yeah, thanks for that fantastic presentation, Arco. It's a nice introduction to what I'm going to talk about today. We're going to take a slightly different view, and we're going to look at citizen science approaches and how we can use these new technologies to help us understand things like coastal change. So I'd like to acknowledge all my collaborators, the Victorian Government, University of Melbourne, and the team from Deakin University that have really helped shape this program and made it what it is today. So thank you for that. So, you know, understanding our coast, that's a global issue, right? Where there's lots of issues with erosion everywhere, every country we go to pretty much. And, you know, understanding what the coastline is doing now and the behaviour of that coast into the future is going to be so important for adaptation and resilience in terms of what we're going to do with things like a rising sea level and a changing climate. For example, we've seen over a 5% increase in significant wave height across the Southern Ocean, which is causing some issues along our coastal zone. So how do we, you know, make the decision of whether we do nothing? Do we do an alignment? Do we hold our position? Do we move seaward? Do we build hard defences? You know, really, to be able to make these types of management decisions, we need to understand how things have changed in the past and how they're tracking right now to enable us to predict what they may be into the future. And that's where the Victorian Coastal Monitoring Program has come in. And it's really about filling those knowledge gaps in the coastal zone, in coastal observing, providing critical observation data and standardised data, not just for the use of the science community, but for every consultant out there, for example, doing coastal hazard assessment. You know, in the state of Victoria, pretty much every consultant doing a hazard assessment is using some of the data that's generated by this program. And really, it's about making informed, evidence-based decision-making. So this page here is just a link to our story map for the Victorian Coastal Monitoring Program. I'll put the link to that in the chat later on, but it gives you a broad overview of the types of things that we're doing, from wave monitoring to offshore mapping to understand the sediment supply offshore to our citizen science program. That's going to be the focus of our talk today. I should mention prior to 2018, we didn't have sustained observations in our coastal zone that provided information about our beaches. We had no long-term wave monitoring program. We didn't have a network of wave buoys. So this has been a real step change for the Victorian community and has provided new opportunities between partnerships between government and the university sector and also industry. So what do we try to do? Well, this program is about aggregating and analysing data at the statewide scale to develop an understanding of how shorelines are changing, to inform these coastal hazard assessments, and also provide opportunities for co-investment. So, you know, this is being used as a model now to look at a national program that we can actually coordinate coastal observing across the country, bringing in a whole range of elements across NCRIS facilities, which is absolutely fantastic. And what I'm going to be talking about is that small component of the drones and how we use unoccupied aerial vehicles to do this work, and in our case, engage with citizen scientists. So yeah, it's a big program with lots of collaborations and lots of really useful information and research coming out. But really, we're just going to focus on the citizen science program. And I suppose, you know, the question is why? Why do we need this type of data that can be achieved using drones? And I think if we look back to what our opportunities are for understanding shoreline change, you know, we can understand where drones fit in. For example, we can use satellites to understand the position of the coast. But this is an example from Geosciences Australia on the left, using Landsat imagery to pick broad patterns of change that are occurring. On the right, it's another example where we've tied together historical aerial imagery and charts to measure changes in a shoreline from baseline sort of levels. So for us to really manage the coast and understand changes in the coastal zone, there's a few things that we're after, and that's improved resolution, frequency, reduced uncertainty, volumetrics, and possibly the increase of number of sites where we can have central observations to inform the changes that are occurring. So the citizen science program, that's what it's all about. It's focused around the citizens, and we're using off-the-shelf drones, so not the fancy ones that Arco was talking about, and some smart target technology from Aeropoint. So these propeller Aeropoints provide the ability for us to get RTK, high centimetre precision of our data sets without actually using expensive and hard to operate RTK GPS equipment. And the reason for that is because we wanted our citizens to be able to do it. And by providing training to those citizens and providing them the resources, they basically are our workforce, if you like, collecting data in their backyard, pushing that data to the cloud, and then we're providing them a platform through Propeller to be able to allow them to analyse quite complex three-dimensional products with very minimal training. So it's worked out quite well from that point of view. And again, you know, we see drones as a bit of a gap stopper between what we can do with satellites and what we can do in the field. It's actually closing the gap and providing another level of information to help inform what's happening on the coast. So just a little bit about the program. We won the Eureka Prize in 2020 for this program, and we've engaged over 180 citizens, and we've got over 400 sites now. Over 700 surveys have been undertaken, and over 2,700 individual flights. That's not bad when you think about a program that's commenced in 2018. So for some of these sites, we have high resolution volumetric data over 2 kilometres of coast for over 4 years at every 4 to 6 weeks. That incredible amount of data that we can mine using Python scripting and automated approaches that is giving us an idea of what's happening in terms of change. We provide training to these citizens as well, and we can actually safely report that our record's going quite well. We have 0 reportable matters to CASA. We've had 5 routinely reported matters, which involved equipment malfunctions and 2 of user error, but relatively small considering the volume of data that has been collected by our citizen scientists. And I'll provide these links in the chat later on, but they're the links to the portal that you can access. Again, you know, amazing community. Our contacts came through the Department of Environment and Energy, Environment and Climate Action, through their contacts, through Facebook group, through local land managers, and through our traditional owners. And I'll talk a little bit more about that shortly. So these are groups on the ground in their backyard. You know, how are we going to possibly get scientific crews to 40 sites across the state at, you know, surveying at 4 to 6 week intervals and picking weather windows and suitable tides? It just wasn't going to happen. So this was a fantastic way to fill those knowledge gaps for our region. So in terms of training and what we do, we're flying under the CASA excluded class operations, and we provide a series of training that includes theory as well as practical training for all our citizen scientists, and just the usual rules about flying drones and making sure that everyone's enabled to be able to do things safely and be able to collect the data in a repeatable fashion. You know, and what we have also found is that with the appropriate training, and we've published a paper on that, and you can access our monitoring manuals and training manuals as well through that paper, is that citizen scientists can capture survey grade data. As good as a scientific team, as good as a consultancy firm, they're able to produce quite good quality data, as long as you've got the right protocols and QA/QC procedures in place. And that's really what this slide is sort of enabling. And, you know, again, enables us to scale up these monitoring programs. And obviously there's a whole lot of other benefits from that science engagement. The engagement in this program has been enormous. And, you know, these citizens really own this program. They are the backbone of the program and they own it, which is fantastic. A little bit about precision. We've done a lot of work ground truthing this data using high precision GPS units and ground control, and you know, this is some work from Nicholas Pacino, who looked at the operational you know, range of data in terms of error assessments for our drone program. And you know, citizen scientists are pretty good. They're not too bad. They're kind of in the mix in terms of the vertical accuracy that we can achieve using this technology, which is fantastic. We're doing a lot of work with traditional owners, but a lot of those owners originally engaged in the program through our coastal monitoring groups, and they still do today. But we've had additional requests for on-country training to enable basically the control of traditional owner data capture of cultural heritage sites of significance. They wanted the ability to capture data on their own terms and the ability to manage that data as well. So we've expanded the program to enable that, which has been really exciting. And we're in the middle of training a couple of extra groups with the Eastern Maar and the Gunner in March this year, which is great. Just if you're thinking about engaging traditional owners, I thought I'd put a bit of a 101 about our experiences. And it has been an incredibly rewarding process, but I think it's really important to develop an Indigenous engagement plan, set your objectives, roles and responsibilities, community engagement and Indigenous cultural and IP protocols. And, you know, some of the things that came up with our groups is, you know, they're really interested in supporting and finding new opportunities for long-term investment employment for their community, and about how we protect the rights in terms of their data, and really, you know, keen in developing these long-lasting partnerships that have been of huge value. And, you know, we've found that work has extended to beyond the coast. We do a lot of seabed mapping. You actually have to map the seabed to understand what's happening on the coast, because, you know, the sediment supply on the coast is impacted by sediments out offshore down to the wave base, which is, you know, 50 to 80 metres. So when we're out there mapping these areas with our seabed mapping technology, we also seen sites of cultural significance, ancient land bridges, extensions of lava flows of culturally significant sites that would have supported our Indigenous people at lower sea level stands. So a little bit about what we're doing with the data. And here's an example of some work that we did at Demon's Bluff. And this is looking at cliff retreats. In fact, the cliff retreat was such a problem at this site, people were actually banned from walking on this beach. I think it's the first permanent ban of the beach access in Australia. And you can see here on the left, we've got some point clouds, and the blue indicating where we've had growth, if you like, of the cliff. That's actually the cliff leaning. And in the bottom image, you can see red, which is showing areas of loss. So we're able to pick up the leaning of the cliff before these sections of cliffs are actually falling onto the beach down below. And we're using multiple data sources to understand long-term trends. So we're delving back into our satellite imagery, historical aerial imagery, and drone data to put all these pictures of the puzzle together. So that's been quite exciting for the work that we're doing, to be able to bring all these different multi-scale data sets together to understand the processes occurring at locations like this. It's really important for informing coastal management. Using these different data sets from coastal drones, but also our seabed mapping and sediment sampling, we can develop these models to understand what's likely to happen in our coastal zone under different management scenarios. And this is some work from Jack McCarroll at the Victorian government. And, you know, he's part of our program, and, you know, we've trialled a couple of different options here for doing nothing, renourishment, or putting in a seawall, and what that may look like. In particular, in a coastal area where we have some historical landfill sites that are likely to be exposed in changing climate. It gives us the ability to work across compartments. So we're able to downscale our drone data and understand what's happening right on the beach level in our tertiary compartments, down to the beach or embayment level, scale it up to much larger secondary compartments, to what we call these sort of primary compartments. And what that means, by combining these different data sets from satellite, drones and aerial photography, hydrodynamic data, and also morphology and structures of our coastline and surrounding seabed, we're able to put these pictures of the puzzle together to understand what's happening on our coast at the coastal statewide level. So in this case, we're able to pull it together and understand how the beaches are changing through time and identify almost an early warning system of where these beaches are tracking and what's likely to happen. So it's showing us, where we've had erosion in the red and accretion in the blue, and we're actually picking up this pulse across the whole state at these sentinel sites. We're able to combine this data also with other products to understand rates of erosion across the state through time. And in this case, we're seeing that there is significant erosion occurring in Victoria, actually above the national average, with 21% of the coast seeing over a 0.31 metre per year change at the moment. So, and a lot of the change that we're seeing is on the open coast. We're actually finding that our embayments are actually accreting sediments. And we're seeing that there's some correlation here with our wave climate, but some of the likely drivers are probably more driven by the estuarine sort of morphology or the compartmental morphology of these locations. The other thing that Arco sort of touched on is that these drones are really important for validating these products, these national products, if you like, or what we can do with satellite imagery, for example. And in this paper by one of our PhD students, Nicholas Puccino, he was actually able to use our drone data, actually identify the time that we collected drone data that coincided with Sentinel-2 satellite overpasses. And he was able to use wave data from the integrated marine observing system and develop these elevation datum shorelines from our drone data that we're able to use to validate shorelines extracted using a variety of techniques, including machine learning from these satellite products. And it's great to see groups like Geosciences Australia, in this case Robbie Bishop's paper, uptaking this citizen science data to validate some of the approaches that they're using as well for national product generation. So I've talked about a lot of the physical stuff we're doing. We think citizen scientists have a fantastic opportunity to apply this technology in the coastal zone in other applications. For example, in this case, monitoring intertidal reef habitats. And we're currently doing some trials with citizen scientists to map these intertidal habitats at low tide. And this really provides some exciting opportunities for us to scale up what we can do with ground truthing on the ground. So I'm a bucket ecologist by trade. I used to go out there with a quadrat and count things in a quadrat. And now drone technology provides us the ability to actually do a full population census across the entire platform. And that really changes what we can do in terms of monitoring in our coastal zone. And you can see here a plot between drone data and ground truth data, and it does work quite well. We're able to use that data to, for example, identify, in this case, Homozyros necklace. Neptune's necklace is a really important habitat-forming algae. And, we're able to sort of map this and monitor changes through time and understand what's driving the distribution of species like this. So just in conclusion, UAVs provide new opportunities in the coastal monitoring space. And, citizen scientists, I think, can play a really important role in that. They enable scaling of programs. The flow of benefits from empowerment are just huge, and they have been incredibly rewarding to see. And, because these coastal systems are so dynamic, they require monitoring through space and time, and we need to use a variety of sources to be able to do that. And I thought I'd leave you with this quote from Santiago Ramon de Cajal, and it really highlights the importance of data collection. Hypotheses come and go, but data remain. Theories will desert us while data defends us. So our true resource, our real estate, and our best pedigree. So if you are out there collecting your data, make sure you preserve it. Make sure it gets up to these national programs such as NCRIS, so that researchers and other users can make use of this data into the future. So thanks very much for having me. And I think we're now going to go over to Karen.
Really excited to talk to you today about how I think drones have become a critical part of our Earth observation portfolio. I wanted to start with just a little bit about my backstory. So I'm really interested in the Great Barrier Reef, and since the late 90s I've been working to answer just one question, and that's how much live coral do we have on the Great Barrier Reef? Because actually we really don't know, and in some ways that's kind of surprising, but in some ways not. And this is really critical for us to understand. So one of the things that I'd like to do is just sort of have a look at, so the Great Barrier Reef, it covers this area along the Queensland coast. It's about 2,500 kilometres, and altogether the Great Barrier Reef Marine Park covers an area of about the size of Victoria plus Tasmania put together. So when you think of it like that, in such a large area, it's not really that surprising that we don't know how much live coral we have, but we really need to get to having that baseline understanding so we know how things change over time. So I want to go into the southeast corner of the Great Barrier Reef, and I'm going to take you into Heron Reef, which is where I started doing a lot of my research in the late 90s. So here's the reef here, here's the island. It's about 800 metres long by 400 metres north-south. The University of Queensland has a research station here, which is why I got started working on heron here. There's also a resort, but it's a really magnificent place to work. Now, as I come in, I'm going to zoom all the way into this, and so we're looking at commercially available satellite data here, and I'd just like you to think of the question, can you see how much live coral we have? And even for an untrained eye, you can probably understand that it's kind of difficult to distinguish the differences that we have here. We know some of it's coral, some's live, some's dead, some's algae. And so this is what we get with satellite data. And for me, this is really important as to why I started getting into drones, because this is the information that we can get from drone data. So from a number of different reefs around the world here, both deep and shallow reefs, you can start to see all the different patches of live coral here. As we come across, you can see that the conditions are different. So sometimes it's a little bit ripply and we don't see it quite so well, but the beautiful colors are really standing out, and we can start to see different genus in some of these images as well. And I really like this one. I just sort of think of it as being like a big smorgasbord of confetti, and it's just really, really beautiful. And that information is just not in the satellite data. Even when we come to some of the images like this, I can start to count individual sea cucumbers. And I'll make the link for this presentation available as well, so you can zoom in and have a look for yourself and really interact with us too. From some deeper data there as well, we can see that even in the deep water when it's quite blue, we can distinguish the individual patches on the reef. So what are some of the other benefits about using drones? Well, I've already shown that we definitely get a lot more detail from the drone data. So satellite data on the left-hand side, this is Planet 5-meter satellite data. And on the right-hand side here, you can see the difference with the drone data and how much detail we see both on land, but in the water as well. So we're much, much closer to the features of interest. Now, it's also really easy for us to just get out and fly when and where we need. Now, this might be important if we're thinking about tidal areas, for example, and it's really important to get data at a particular time of day. You don't have to worry about specific satellite overpasses. Now, I also really think it's important to think about some of those weather conditions where we can't capture satellite data. Yes, we might be able to get radar data, but optical satellite data is a real pain in disaster situations if we need data then and there. But hey, it's cloudy, so we just don't get that information. With drones, we can fly underneath it. I also like that you can pick up a drone from your local electronics store, JB Hi-Fi, Harvey Norman, and you can get out and get started. These things are really quite small, and it's quite easy to get started with that. So anyone, anywhere can start to capture these data. And finally, we have some really cool data processing that we can do that allows us to look not just at the imagery itself, but we can also extract these 3D models. And so in this case, I'm really interested in looking at the terrain, and we can start to see how the elevation changes over the areas. We can get this three-dimensional texture. We can look at the height of trees or even corals if we're interested underwater as well. So some really interesting processing techniques that we can use with drones that again just aren't available to us with satellite data. One of the other reasons I really like working with drone data is because I see some really great opportunities for calibrating and validating our satellite data modeling. So whether that's global land cover, or in this case, in the Allen Coral Atlas, looking at the coral reefs of the world. Now this works on a global scale, but how good is it on a local scale? So I recently spent some time in Belize, and I'm going to come into this area here and look at the classification from the Atlas compared to our drone data. And so what you'll be able to see is that although we're looking at the same types of categories, so for example, the pink here is coral, green is seagrass, rock, rubble, bit of sand, and this is representing the island here. When we peel away the classification based on 5-meter satellite data and we look at what the drone data looks like underneath, that it's actually quite different. So for example, based on fieldwork, I know that this area here that's covered in pink as coral is actually all seagrass along here. This is all seagrass here too. The island is a very different shape to what satellite data would have us believe because of that resolution issue. And the satellite modeling also stops when the water gets a little bit deeper, but we can actually see that there still is some coral there as well. So what implications does this have for any management decisions that we're making and any interventions that we may need to do? But so one of the other challenges is that the satellite data are fantastic for really, really broad areas. And we get a good idea of this here. Again, this is the planet data, but then we zoom into drone data and then it's not necessarily enough as well. So it's just part of the portfolio of Earth observation. We have some snorkel data taken just below the surface, and then we zoom all the way in to some dive data as well. And you can actually see some calibration targets. You can see our field site and some gorgonians or soft corals here. So this is just all part of the package where everything works together. Back to our snorkeling, our drone, and then all the way out to our satellite data as well. But so one of the challenges is that we can't do field data everywhere. So it might get us the detail that we need. But what I'd like you to take away from this video here is really this feeling of scale and how teeny tiny Dr. Javier Leon is as he's snorkeling along the reef here. His buddy's just about to come into view. And as we pull out, you'll just see the scale of just one of 3,000 reefs of the Great Barrier Reef. In this case, this is Heron Island. So you really should appreciate that field data just isn't possible everywhere. But we can't drone everywhere either. And this is sometimes how I feel. I feel kind of small when I'm out there droning. And so this, for me, where global collaboration comes into play. And in this case, we can have a look around the world that there's people using drone data for all sorts of Earth observation reasons. And so, for example, we've got Renee Bartolo working in Kakadu National Park. We have collaborators in India and Nepal. We can go up to Northern Europe, and in this case Poland, and look at some of the glaciers and other really, really cold areas around the world that maybe we don't necessarily get the opportunity to get to. We can come into the US, and again, we've got, in this case, some urban infrastructure. What about if we head on over to Africa? In this case, we're hitting Uganda and looking at urban infrastructure there and what the differences are as well. Or even into South America, where we're looking at post-fire and some challenges that we have in the ecosystems over there. But so one of the challenges that I then experienced was I know that there's people around the world doing this sort of work that's quite similar to what I do in all sorts of different ecosystems. But how can we make the work that we're all doing findable, accessible, interoperable, and reusable, or fair? And so I came up with this idea that what if we actually made it really simple for people to contribute and really work together in this way? So the case is here. We capture our data, relatively simple to start with. Once we've got all of our raw drone mapping images, all these overlapping photos, we upload them into a central repository. At that point, the platform auto-mosaics your data. So it then makes it available out of like a map here with all the metadata that it's either extracted or you've input for yourself there as well. And it's all stored together. And you can store your own data and share it in this way as well. So in this case, this is my profile. I've got data over here in Belize, some data around here in Australia. So I see it as dots on the map and I see it in my table of contents. But if that's not enough for what I'm doing, or if I'm unable to collect data for myself in certain locations, I can actually go around the world and access other people's data as well. And so that's really cool if I need to start thinking about, well, what are other data sets that I might need to test and adjust there as well? I can refine that specifically by a type of ecosystem. And in this case, we're using the IUCN habitats. So we've got all the different categories, and I could say, well, maybe I'm working in grasslands in this case. I can see all the different data sets that are there. Perhaps I've got an AI model that I've tested in my local area, and I need to see if it's going to scale to other areas, other geographies around the world there as well. And then one of the cool things is that not just looking at platform access, we're then able to stream directly into other systems, so other GIS that you're using there as well, which is really important when you want to continue analyses there in your own packages as well. And so to me, this all comes down into what I'm trying to build, which I like to call the circular data economy. And if we think about the way we work in our daily lives, in other aspects outside of data, a lot of the time we're trying to move away from a linear economy, which is where we have products and materials that are created or manufactured, consumed, and then discarded. That's linear. So what we try and do is to work more into the reuse, recycle, upcycle. And so by doing that, we're keeping our products and materials in circulation for far longer. And that's what we call a circular economy. So I'm really interested in how we apply that to the data that we capture as well. So we build a system where you can capture the data, contribute it to a global repository, and then we curate that as well. So bring it all together in one place for people to access via that FAIR system that I mentioned. It enables people outside your own immediate network, so anyone around the world can create something with those data. So they can develop insights and management decisions, and then build collaborations as well, and then feedback into other areas where we might need to capture more data too. So in this way, we're really believing that all data has a life beyond that for which it was initially captured. And if we can all work together, we're really building an awesome system that we can use to continue building insights and making better management decisions in the long run. And I think in the words of Sir David Attenborough, I think he put it perfectly. If working apart, we're a force powerful enough to destabilize our planet, surely working together, we're powerful enough to save it. Thanks so much for listening.
Wow, I think everyone have to agree. We've had 3 very passionate speakers, and if they can now turn on their videos, we have I saw Joan and Paul, if you can turn on. So as we mentioned earlier, Karen did a fantastic job presenting that from Magnetic Island in the field, but she's not here to answer the questions. So Paul Mead and Joan Lee are representing her, and we have some questions yet to be answered. So just quickly, Mark Westerby has asked you, ARCO. I don't know whether you've answered that one or not. Hang on, I've just got to find it. Maybe you can just have a look for the one in the chat, ARCO, that didn't get into the Q&A, while I also ask Dan the one that's from Chris Drummond that's in the Q&A that says, were you prescriptive about camera settings similar to ARCO's protocols?
Yeah, look, that's a good question. We wanted to standardise the program so everyone used the same model drone in the citizen science program. So they were people phantoms, they were flying at exactly the same height, and we gave them the same predetermined flight path to use every time as well. So we were certain of the area of interest was going to be captured through all those survey runs. And so yes, we did. And you know, with the ground control, the smart target technology really changed what we could do in terms of precision for these community groups, and just simplified the ability to collect that type of data without having more complex RTK GPS units. So hopefully that answers the question.
And you can download, the protocol? You can download.
I believe so. I'll double check. I just noticed it's not on our story map. It should probably be there, but it's linked with the paper. So if anyone does want it, email me direct and I'll make sure that you get a copy of it. But if you have access to that journal article that I posted, you'll have the training protocols as part of that.
Thank you. And Arco, did you track down Mark's question?
I did, Beryl, and I did post an answer to Mark's question.
Okay.
Yeah, just in the chat, not in the Q&A.
Okay, thank you. I missed all that. So Paul and Joan, on behalf of Karen, I've got a question. So, you know, for drone technologies to reach their full potential and support understandings of landscapes and so on, we're going to need lots of systems to support the storage and analysis and sharing. And there was a little bit in Karen's talk about that. But what are your thoughts about doing it in an open access form, given that some of the data will be sensitive and a lot of it's collected from people's personal drones, and so there might be some resistance to them making that openly accessible and giving people a bit of a head start in their research when they went to the trouble of investing. Any comments from either or both of you?
Yeah, sure. Thanks, Beryl. It's a great question. And I think, you know, the first one is, you know, when you think about how many researchers we have out in the field every day collecting data on our at-risk ecosystems and how much money is invested, is that a lot of the time they're collecting the same types of data, or even data of the same ecosystems, but there is that lack of collaboration. You know, we just look at how many scientists and researchers are out on the Great Barrier Reef, for example, each year. And I think that we can be more effective in our spend of time and money if we know where that data is from the first point. But we can also then speed up our collaborations because we are in a race against time with some of our at-risk ecosystems. And so collaboration does bring that speed to us being able to solve a lot of these problems. And we've got to have that data, you know, as we talk about being fair, findable, accessible, interoperable, and reusable. I think, you know, there is that question of, oh, but what if someone gets to publish in the Nature journal before I do, before I've had to use my data? I think that, you know, maybe researchers devalue their own worth there at sometimes, and what else they bring to their research. It's not just their data, you know, that there is all of these insights and that mountain of work that they've done beforehand to get to that stage and to provide those insights on their data as well. But certainly there are cases where data has to be private. You know, we work a lot with Indigenous groups where they have culturally sensitive data, and that has to be protected. They have to have that data sovereignty. And so, you know, GNIDEA has that ability to make data sets private, but also to allow them to choose when and how they want to share that data so that they maintain control of their data. So, yeah, hopefully that sort of answers that sort of side of things, Beryl, for you.
Thank you. And we'll pick up Andrew Walsh's question offline because we are at the end of our time. And I do want to thank our speakers again for everything that they've done. It's been a fun hour. So, and a great audience and all the great questions. So we have a few to follow up. We will do that, but we want you to come again. And our next webinar is on Wednesday, the 3rd of May, which will be all about bioindicators. In the use of assessing ecosystems. So we will leave you all exactly on time. Thank you very much, and we'll hopefully see you again soon. Thank you.